Well, welcome back to our course on algorithms and data structures. And this will be our final lecture as we cover this material. And the last lecture, we talked about graphs, and this will be a little bit of a shorter lecture, but we'll be talking about graph implementations. And so here is a listing of the contents in this chapter from the textbook. We'll do an overview of two implementations. We'll have a little more discussion of vertices and edges, and then we'll talk about an implementation of the ADT graph. So like the ADTs we have seen previously, graphs have several implementations. Each implementation must represent the vertices in the graph and the edges between the vertices. In general, you use either a list or a dictionary to hold the vertices, an array or a list to represent the edges. Each representation of the edges has its own advantages, but the list representation is most typical. So let's have an overview of two implementations. Two common implementations of the ADT graph use either an array or a list to represent the graph's edges. The array is typically a two-dimensional array called an adjacency matrix. The list is called an adjacency list. Each of these constructs represents the connections, that is, the edges among the vertices in the graph. So let's talk about the adjacency matrix. So the adjacency matrix for a graph of n vertices has n rows and n columns. Each row and each column corresponds to the vertices of the graph. You number the vertices from 0 to n minus 1 to match the rows indicated by the column indices. If Aij is the element in the row I and column j of the matrix Aij indicates an edge exists between vertices I and j. For an unweighted graph, you can use Boolean values in the matrix. For a weighted graph, you can represent edges. You can use edge weights when weights exist in a representation of an infinity otherwise. So in figure 31 that we're showing here it provides an example of an unweighted directed graph and its adjacency matrix. Let's consider vertex A of the graph, which we have numbered as vertex 0. Since the directed edges exist from vertex A to each of the vertices B, D, and E, the matrix elements A01, A03, and A04 are true. We have used a T in the figure to represent true. The other entries in the row are false, which are blank in the figure. For the adjacency list, an adjacency list for a given vertex represents only those edges that originate from the vertex. In figure 32, which we're showing here, each vertex of the graph in figure 31a references a list of adjacent vertices. Space is not reserved for edges that do not exist. Thus, the adjacency list taken together use less memory than the corresponding adjacency matrix in figure 31b. For this reason, implementation of sparse graphs use adjacency lists. The implementation that we present in this chapter will do so also, since typical graphs are sparse. So vertices and edges. While designing a class that implements the ADT graph, we encountered two types of objects, the vertex and the edges. These objects are interrelated. A vertex has edges that leaves it, and an edge is defined by the vertices at its end. A vertex in a graph is something like a node in a tree. Both vertices and nodes are implementation details that are hidden from the client. In the implementation of a binary tree, we used a package-friendly class binary node. So reminder, see segment 25.2 of chapter 25. Here, a graph will have a package access to the class vertex. Previously, we simplified the implementation of a binary tree by giving binary node more than a simple accessor and mutator operations. The same is true now for the implementation of the ADT graph. In fact, the specifications of the ADT graph that you saw in the previous chapter, segment 2925, omit the operations necessary to implement various graphs algorithms. We assign these operations to the vertices. The structure of a vertex is more like the structure of a node in a general tree than a structure of a node in a binary tree. Both the general node in figure 25.8 and a vertex reference a list that you can use to address other nodes or vertices. So let's talk about specifying the class vertex. For identifying vertices, first we need a way to identify the vertices in a graph. One simple way is to use either integers or strings. A more general approach, the one we used in the previous chapter, labels each vertex with an object. The label will be a data field of the class vertex. One operation of vertex that then is to retrieve a vertex label. We'll use the constructor to set the label, omitting a mutator method for the field. For visiting the vertices, the algorithms that we discussed in the previous chapter require us to mark certain vertices when they are visited. We therefore give operations to vertex that make a vertex as visited, tested whether a vertex has been visited, or remove the mask. Then for the adjacency list, as we mentioned earlier in this chapter, a vertex adjacency list indicates its neighbors. Rather than placing this list within the class of graphs, it is more convenient to make it part of the class vector. Soon we will define a simple class edge whose instance we will place in these adjacency lists. Thus, a particular vertex adjacency list contains the edges that lead the vertex. Each edge indicates its weight, if any, and references the vertex that ends the edge. Vertex then needs methods to add edges to the adjacency list. These methods essentially connect a vertex to its neighbors. In addition, we must have access to the adjacency list for a given vertex. Thus, we define an iterator that returns our vertex neighbors, as well as the iterator that returns the weights of the edges to those neighbors. For convenience, we also include a method to test whether a vertex has at least one neighbor. As you can see, the adjacency list is the only place where we need an instance of edge. Thus, edge is the implementation detail that we can hide within vector as an inner class. For the path operations, while finding a path through a graph, we must be able to locate the vertex that comes before a given vertex on a path. In other words, a vertex predecessor. Thus, we need set, get, and test operations for a vertex predecessor. Certain algorithms find the path with the shortest length or the path that has the smallest weight or cost. A vertex can record either the length or the weight of the path from the origin to a cell. Thus, we have operations that set and get the recorded value. And for the Java interface, the interface in listing 31 that we're showing specifies a vertex operation that we have just introduced. The generic type T represents the data type of the objects that label a vertex. Okay, for identifying the vertices, first we need a way to identify the vertices in a graph. Hold on just a second. This is just a continuation of this listing, so I'll just quickly you can scan through this if you like, and at your leisure you can come back to this and look at it later. So I'll just go on from here. Here is the third part of this, and so once again you can just scan through that quickly and see the various elements. And finally, here is let's talk about the inner class. As we mentioned, we place an instance of the class edge in a vertex adjacency list to indicate the edges that originate at the vertex. Thus, each edge must record both the vertex that edge ends it and the edge's weight, if any. Recording an edge weight is the only reason we need a class of edges. For unweighted graphs, we could simply place vertices in an adjacency list. Using edge objects, however, allows us to use one class of vertices for both weighted and unweighted graphs. Since vertex is the only class that uses edges, we make edge an inner class of vertex. Listing 32 that we're showing here shows an implementation of edge. We provide a data field for the edge's weights, if any. For unweighted graphs, we will set the field to 0 rather than creating a class of unweighted edges. Note that the edge's second constructor sets the edge weight to 0. So here's a outline of the implementation of the class vertex. To hide vertex from the clients of the graph, we place it within the package graph package that we introduced in the previous chapter. Listing 33 that we're showing here outlines the class and shows its data fields and constructor. An ADT list that has an iterator serves as an adjacency list edge list. We have chosen the linked implementation linked list with iterator discussed in segment 13.9 of chapter 13. So this is just a continuation, and so you can look that over. Let's talk about the two connect methods. Each method connects as specified by vertex interface in listing 31. Places an edge into a vertex adjacency list. We first implemented the method for weighted graphs and then used it to implement the method for unweighted graphs, preventing the addition of an edge that either exists in the graph already or connects a vertex with itself consumes most of the method's efforts. Once those details are complete, connect simply calls the ADT list add method to add the edge. For the iterators, the method getNeighbor iterator returns an iterator to a vertex adjacency vertices, that is its neighbors. We define a private interclass neighbor iterator within vertex that implements Java's interface iterator. Thus, getNeighbor iterator has the following implementation. The class neighbor iterator appears in listing 30-4, which we're showing here. Its constructors establish an instance of the iterator defined in linked list with iterator. The method next uses this iterator to verse the edges in the vertex's adjacency list. Then using edges method get and vertex next assesses the neighbor's vertex and returns it. For the methods has neighbor and get unvisited neighbor, the method has neighbor uses the method is empty of linked list with iterator to test whether the edge is empty. The method get unvisited neighbor uses the iterator returned by get neighbor iterator to return an adjacency vertex that is unvisited. This task is necessary in a topological sort. For the remaining vertices, vertex should override the methods equal. The two vertices are equal if their labels are equal. And so the remaining methods of the vertex have uncomplicated implementations, and you can work on those on your own as you would like. So in terms of an implementation of the ADT graph, we now consider how to use the vertex as an implementation of the director graph that can be either weighted or unweighted. In terms of basic operations, whether our implementation uses an adjacency list as we will here, or an adjacency matrix, it must have a container for the graph's vertices. If we use integers to identify the vertices, a list would be a natural choice for the container, since each integer could correspond to a position within the list. If we use an object such as a string to identify them, a dictionary is a better choice than and that is what we do here. In terms of a note, Regardless of the kind of graph or how you implement, you need a container such as a dictionary for the graph's interface. You might want to keep that in mind. For implementing a graph operation, figure 33, which we're showing here, illustrates a dictionary of vertices for a small directed graph. Each of the vertices A and D has an adjacency list of the edges that originate at that vertex. The letters within these edges represent references to corresponding vertices within the dictionary. Since the ADT dictionary consists of key value pairs, we can use the vertex label as a search key and the vertices themselves as the corresponding values. The organization allows us to quickly locate a particular vertex given its label. Our class begins as shown in listing 30-3. Recall that the generic type T represents the data type of the objects that label the graph's vertices. The class first data field is a dictionary of vertices. A count of vertices is not necessary since the dictionary will count the vertices for us. Since each vertex maintains its own adjacency list, the edges in the graph are now easily counted. Thus, we should maintain an edge count as a data field within the graph class. For adding vertices, the method add vertex uses vertex constructor to create a new vertex. It then adds a vertex to the dictionary by invoking the dictionary method add. For adding edges, methods such as add edge that identify an existing vertex by its label must locate the vertex within the dictionary vertices. To do this, they invoke the dictionary method getValue using the vertex label as the search key. Having located the edge vertices that delineate the edge to be added, add edge adds an edge to the adjacency list of the origin vertex. It does this by invoking vertex connect method. If the edge is added successfully, edge connect is incremented. Thus, our graphs add edge methods have the following definition, one for weighted graphs and one for unweighted graphs. For testing for an edge, the method hasEdge begins like addEdge by locating the two vertices that define the desired edge. With the original vertex in hand, hasEdge invokes vertex method getNeighbor iterator and searches the origin's adjacency list for the desired edge. In the following implementation, you can see why defining the equal method in vertex is important. So for miscellaneous methods, the methods isEmpty, clear, getNumber of vertices, and getNumber of edges have the following simple implementations. And so those are things that you can be thinking about. For resetting vertices, you saw in segment 3011 that the class vertex has data fields visited, previous vertex, and cost. These fields are necessary for the implementation of the graph algorithm that we introduced in the previous chapter. Once you have searched a graph for a shorter path, for example, many of the vertices will have been visited and marked accordingly. Before you could perform a topological sort on the same graph, you would have to reset the field visited for each vertex in the graph. The following method, reset vertices, sets the field visited, previous vertex, and cost to their initial values. To do so, the method uses one of the iterators declared in the interface dictionary interface. The method is not public as it will call it only from the method declared in graph algorithm interface. For efficiency, adding a vertex to a graph is a big O notation and operation since the vertex is added to a linked dictionary. Adding an edge involves retrieving two vertices from the dictionary and then calling vertex method connect. Thus, the method addEdge is also big O, and likewise hasEdge is big O n as it first retrieves two vertices from the dictionary. It then iterates through the edges that leaves the first vertex to see whether one of them ends at the second vertex. As you can see, the performance of these three graph operations depends on the number of the vertices in the graph. The remaining method in basic graph interfaces are each big O1. Figure 30.4 summarizes these observations, and that's what we're showing here. For a breadth first traversal, we're showing a listing of that. Segment 2912 of the previous chapter presented an algorithm for a breadth first traversal of a non-empty graph beginning at a given origin vertex. Recall that the traversal first visits the origin and the origin's neighbors. It then visits each neighbor of the origin's neighbors. The traversal uses a queue to hold the vertices as they are visited. The traversal order is the order in which vertices are added to the queue, but since the algorithm must remove vertices from the queue, we maintain the traversal order in a second queue. Since the second queue is returned to the client, we enqueue vertex labels instead of vertices. Remember that the class vertex is unavailable to the client. The following implementation of the method getBreadthFirstTraversal closely follows the pseudocode given in the previous chapter. The parameter origin is an object that labels the origin vertex of the traversal. So in terms of the shorted path, I'm thinking about a implementation of that. So the shortest path of all paths from one vertex to another is an unweighted graph, is the path that has the fewest edges. The algorithm that finds this path, as you saw in segment 2919 of the previous chapters, is based on the breadth first algorithm. When we visit a vertex V, we mark it as visited. Note that vertex P that precedes V in the graph, and note the length of the path that the traversal followed to reach V. We place both this path length and reference to P into the vertex V. When the traversal reaches the desired destination, we can construct the shortest path from the data in the vertices. The implementation of get shortest path closely follows the pseudocode given in the previous chapter. The parameters begin and end are objects that label the origin and destination vertices of the path. The third parameter path is in an initially empty stack. At the conclusion of the method, the stack contains a label of the vertices along the shortest path. The method returns the length of this path. Okay, this is just the conclusion of that listing. And so you can look that over at your leisure. And with that, that concludes this lecture. And also this is the last lecture, what we'll be doing for this class. So thank you very much.